Hello and welcome to this lecture. Over the past few lectures, we have derived the governing equations of mass, momentum, energy and species conservation for an incompressible Newtonian, that is linear Stokesian fluid. And so we are now in a position to apply these governing principles to develop mathematical models of specific problems, and by analyzing these models to understand the physics of these problems that we take up. Now, in this process of analysis of transport problems, there are several techniques that come up time and again and which are extremely useful in understanding the basic physics of a problem, short of having a complete solution. And one of these techniques, a very important one, is scaling and non-dimensionalization. And so that's what we will take up in this lecture. Scaling and non-dimensionalization. Now, non-dimensionalization can be done in several ways, and scaling is a particular way of doing it that allows us to see which terms of our governing equations are small and can be neglected, and which also forces us or helps us to understand the governing physics of a problem. And we shall see this as we go along. Now, the best way to understand these techniques is to actually work out an example and see these methods and techniques at play. And so that's what we will do today. Take a specific example and apply scaling and non-dimensionalization. So the example we will take is that of flow in a microchannel, where the flow is driven by both a pressure gradient as well as by electro-osmotic flow at the walls. So it's scaling, which is going to be shown in the context of electro-osmotic, pressure driven, write it more clearly, pressure driven flow in a microchannel. All right. So what's the problem of interest now? So these days you have a whole range of research and development projects seeking to develop micro-size devices to carry out miniaturized versions of chemical processing, biochemical processing, medical diagnosis, such as measuring the amount of glucose in blood and so on. And all these micro devices contain in them channels, micron size channels. So by that I mean the dimensions are typically anywhere from tens of microns to several hundred microns. And these microchannels have fluids flowing through them. And a key aspect of designing these devices is controlling, manipulating the flow inside these microchannels. So the reason this problem is interesting is that once you go to the micro scale, the key balances of physical forces start to change. So at the small scales, surface forces dominate, like surface tension, charge effects at walls, and so on, start to dominate over body forces like gravity and inertial forces in the fluid. And that we will see is the case in the example that we take today. All right, so to be concrete, we're interested in flow through a channel. We shall work in 2 dimensions for simplicity. So let me draw a schematic here. Consider a planar channel. So in reality, this might be a rectangular channel, but we are just going to, so it might be a rectangular channel, but we are just going to look at the midplane for simplicity in 2 dimensions. All right, so these are the walls of my planar channel, and these walls are going to be made of glass, let's say. So it's a glass microchannel, and through this channel we have a fluid flowing. Some liquid is flowing through the channel. Now, if you have purely pressure driven flow, we know that this is simply Poiseuille flow between parallel plates and we expect a parabolic velocity profile. This is something that you would have derived in your earlier class on fluid mechanics that you might have taken. But what we're going to look at, which is a little beyond that and which is particularly relevant for microchannels, is the influence of an electro-osmotic flow. So what is electro-osmotic flow? So if these channels are made of glass typically, glass is negatively charged. So you have static negative charges sitting inside this glass wall. And the same holds for the wall on top as well. So the presence of these negative charges, if your fluid is an electrolyte, which means it has free ions, then positive free ions tend to accumulate near the wall, forming a kind of electric double layer that tends to shield the bulk of the fluid. So the bulk of the fluid has positive and negative charges sitting together and neutralizes. So it is in effect shielded from the negative charge of the wall by this positive charge of ions that develops near the wall. Alright, so this happens even if you take a large channel of glass, you would also have this electric double layer. However, the effect of this double layer is more prominent in microchannels for reasons which we will see. Alright, so you have this layer. Normally this layer will do nothing much if you simply apply a pressure driven flow across the channel. So here I have P in, here I have P out, and we say delta P is P in minus P out, and this is the pressure difference that's driving a flow through a channel, let's say, which has length L. Right, so this pressure can drive flow. In addition, I can apply an electric field which points in this forward x direction. So let me set up a coordinate system x. The cross channel direction is y. So I'm saying that in addition to the pressure flow, I'm applying an electric field by having two electrodes on either side connected with a potential difference. So the point is, if you now have an electric field directed along the channel, then the positive charges in the fluid near the walls will tend to move. So these positive charges will begin to move near the walls. And this flow is called electro-osmotic flow. Osmotic flow. Why? Because you have an osmosis, so to speak, of the positively charged ions near the wall that tend to move. And they move in the direction of the electric field. Alright, so what you will have now is a velocity profile that looks a bit different from the usual flow between flat plates. In the flat plate flow, you have a perfectly, so let's draw it here. Normally in flow between flat plates, you have a perfectly parabolic velocity profile. But now you would expect that you would have some non-zero velocity at the walls as well. And so your velocity profile will look a bit different. And our objective here is to solve for this profile. But beyond that, we want to use methods of scaling analysis to understand the relative influence of the electro-osmotic or electric field driving force and the pressure gradient driving force on the fluid. In other words, I might want to ask, let's say for a fixed electric field and fixed properties of the glass and the electrolyte, how small should my channel be for these electro-osmotic effects to show up? Will they also show up for a large channel which is a meter in diameter? These are the sorts of questions that we have. In fact, when I use the term small channel versus large channel, you can ask me the extreme relevant question, how small is small? And what do I mean by small? Now, we might have some vague idea that if the channel is very large, then maybe the effects near the wall won't affect the bulk flow. But we need to be more concrete than this, and ideally we would like to have a well-defined condition so that I can say if my diameter is greater than a certain value, I can neglect the presence of this electric field or this electro-osmotic flow. Whereas if it's much smaller than some value, I should instead be in a position to neglect the pressure gradient. And one way to do this, of course, is to solve the problem directly. In this case, we can solve it analytically, but in general, maybe you would have to solve it numerically, and then vary the pressure gradient, vary the electric field, and so on. But these methods require a lot of effort, and they don't give you as much understanding as we will get right now without doing any calculation whatsoever, purely from the method of non-dimensionalizing variables by using scaling analysis. So this is what we're going to do right now. All right, so before we proceed, we need to have a somewhat simpler model. So one way to model electro-osmotic flow is to solve for the charge distribution by solving Gauss's field equations, and then account for the force experienced by the charged particles due to the applied electric field, and then couple that to the equations for flow of the fluid, which also has the pressure gradient. But it turns out that the dynamics of this charge distribution field is much faster than the timescale at which the flow evolves. Essentially, that means is even if these charges move around by the flow, this electric double layer reforms almost instantaneously. So to a very good approximation, you can assume that these the positive charges have a certain thickness in the double layer, and that's a constant thickness layer. And then all you have to do is account for the flow in this fixed layer. Moreover, because this electric double layer is really much smaller, it's at the nanometric scale. So even in a microchannel, this layer is extremely thin. So what people can do is they've, in a sense, averaged out this layer and replaced the effect of the electric charge motion by specifying a slip velocity at the wall. So a simple model for an electro-osmotic flow is simply to consider flow between parallel plates. So these are my walls. I have a pressure-driven flow in the of the fluid, but at the walls I say that there is a slip velocity. In other words, you can imagine a flow where you have flow of fluid, but the walls themselves are moving. So even though in reality the walls are not moving, but a thin layer of fluid moves near the wall. But we can model that effectively if the layer is sufficiently thin by saying that at the walls we have a moving wall boundary condition. So this effectively becomes a kind of mixture between pressure-driven flow and Couette flow where the wall moves. So basically I can say that my the velocity v at the walls occurs in the x direction. So maybe we write the boundary conditions after writing down the equations. So I'll just write this in words. So we have Vs, a slip velocity at the walls. Now it has been shown that this slip velocity boundary condition is called the Helmholtz-Smoluchowski slip, and it can be shown to vary with the strength of the applied electric field and inversely with the viscosity of the fluid mu. So there's a fluid here with, let's say, density rho, constant density, constant viscosity mu, and the electric field goes as E by mu. There's also a factor epsilon called the permissivity, zeta naught called the zeta potential, but we shan't worry about this. The main point is if I increase the strength of the electric field, I'll have a stronger and stronger slip velocity at the wall, and if the viscosity of the fluid is very high, then that slip velocity decreases. This is because basically the effective slip is a competition between the forces exerted on the moving charges and the viscous drag exerted by the wall, which wants to make the velocity go to zero in the absence of the electric field. All right, so what we will do is set this aside. So you know that the physical origin of this slip at the wall is coming from electro-osmotic flow, but mathematically we will just input a constant amount of velocity slip, and our objective is to figure out what is a large value of Vs. So if I say let's consider a case where the slip velocity is small, and then maybe I can neglect it relative to the pressure gradient, you will want to know how small is small. And how can I meaningfully compare the effect of the slip velocity to the effect of the implied pressure gradient? And how does that competition depend on the size of the channel? In this case, the width between the parallel plates, which I will call capital H. Right, and the length of my plate, let's say, is the length of the channel is L, the height of the channel is capital H. Delta P is the pressure drop applied over the channel, and the fluid has a viscosity rho and a viscosity mu and a density rho. All right, so this is the mathematical problem that we are interested in, or the model problem, motivated by our situation of a combination of pressure driven and electro-osmotic flow. Okay, so let's now write down the governing equations for this problem. So I'll just rewrite what we have just derived over the past few classes. So I have the divergence of velocity 0 because I'm going to assume incompressibility. This is perfectly fine for a fluid under these circumstances. And then of course I have the Navier-Stokes conditions. So I have the material derivative here, but I'll write it out in full so you can see the terms. Yes, is balanced by the pressure gradient. So minus the gradient of the pressure, let me use small p to indicate this is the general variable. Del square V, the viscous term. And now I would normally have the gravitational force, but I'm going to neglect it because we are basically looking at microchannel flow where the influences of gravity are weak. However, even if you do take it, you can incorporate this into the pressure by redefining incorporated into pressure. So I can basically redefine dynamic pressure P as the actual pressure, as a difference between the actual pressure and the hydrostatic pressure introduced by rho g. But so this is a simple procedure, it's something you would have probably seen before. But now since our focus is anyway on the scaling, we'll just neglect this term with the understanding that it doesn't change the physics in this problem of single phase flow. Okay, so these are our two equations for the flow, and then we have boundary conditions. So we say the boundary conditions are basically the velocity v is equal to the slip velocity in the x, so it's a x directed velocity with magnitude v slip, and this holds at both y equal to 0 and y equal to capital H, which is the height of our channel. So remember, our coordinate system is in this fashion: x along the flow, y transfers to the flow. Okay, so now we can simplify these equations under the following assumptions. So we are going to assume, or we are going to search, let's say, for a solution which is steady and unidirectional, and such a flow, a steady unidirectional flow, is stable in microchannels because the Reynolds number is small, so that we are very, very far away from any possibility of going turbulent. What is the Reynolds number and why does its smallness suggest stability of such a unidirectional flow? We will address that in the next lecture, as that also has to do with scaling. But some of you all should already know about the Reynolds number, so that's just helpful. And if you don't know about it, then just take my word that in microchannels this is a good assumption, and experiments show that the flow is in fact steady, unidirectional and fully developed. That is, it does not change along the flow direction. In fact, you will see that the fully developed feature follows from unidirectional flow, so I don't have to write it as a separate assumption. Okay, so under these assumptions, let's start to simplify our governing equations. So what does continuity equation give us? Which is the divergence of v is 0. Well, since the unique velocity component is ux, so I'm going to take basically my velocity field is my velocity vector is u v w. So only u is in the ex direction, and only this component survives, and these two I'm saying don't exist because I have unidirectional flow. So then the divergence of the velocity becomes simply dou u by dou x equals to 0. This is I get from continuity. So this implies that u is fully developed. That means u only depends on y. So the x-directed velocity can only be a function of y because as we see from continuity, it cannot depend on x. This of course is only under the condition of unidirectional flow. I'm sorry, w doesn't exist because we are in 2D. Okay, so this is our first equation, which tells me that u is only a function of y. Now I move on to the Navier-Stokes. So what does this become? Remember, I'm looking at steady flow, so that means this term cancels. If I look at v dot gradient of v, the only component that survives is u times du dx. But I know du dx is 0, therefore this term also cancels. So you can see that effectively when we say the flow is steady and unidirectional, we mean that the inertial terms play no role in the flow. And these terms are anyway actually quite small when the Reynolds number is small. That's what it means to say the Reynolds number is small, which is why this is a good assumption for microchannels. Alright, so carrying on from that. So the Navier-Stokes basically tells me that we have 0 is equal to minus dou p by dou x, right, because it's just one direction, plus mu times dou square u by dou y squared. Sorry. Yes, and then I don't have the gravity term. This is my equation. But I can make another simplification here. Remember, du dx is constant. So if I differentiate with respect to x, I will get the fact that mu dou square by dou y square of dou u dou x must be equal to dou square p by dou x square. But I know that this is 0, right, which implies this is 0, which in turn implies that dou p by dou x is a constant, which means I can replace dou p by dou x directly by the applied pressure gradient delta p over the length L, because I know that the local gradient everywhere is a constant. So I can just replace it by the P in minus P out, which is delta P across the entire channel, divided by the length of the channel. So this is effectively by integrating this equation. Okay, so then I can rewrite my final momentum balance equation, which is all that survives now, as mu. I can now use the total derivative because this velocity is only a function of y. D square u by dy squared is equal to delta p over L, and I'm going to keep the minus sign inside because I have defined this delta p to be, because I have defined delta p as p in minus p out. Okay, so this is a positive number, but when I do this integral, I'll usually go out minus in. So I'll actually have a negative sign sitting here. Okay. All right. So essentially, this this quantity here, I mean, it is negative. All right. So now this is our governing equation after simplification for unidirectional flow and steady flow, and this has to be accompanied by our two boundary conditions, which is basically u is equal to Vs at y is equal to 0 and h. So let's call this equation 1a and equation 1b. Now this is a simple linear equation, and the right hand side is independent of y. So one can directly integrate out this equation twice, apply the boundary conditions, and you'd have your solution analytically. And it's something that you have done before, I'm sure. However, our objective here is to use this as an example to understand how to carry out order of 1 scaling, and because that will be a technique that we will find very useful in problems that we cannot solve directly. And even in this problem, you see that this exercise that we are going to, which we are about to undertake, will help us understand the problem at a deeper level. So let us now turn to scaling these equations. So what is scaling? Or to be more specific, yes, so what is scaling? Scaling is the practice of non-dimensionalizing each term of the equations by using, this is the key part, by using a scale factor or a characteristic scale that captures the magnitude of the term. And the point of this is essentially so that the resulting non-dimensional term, so after we scale out the equations, the terms that remain are non-dimensional, and we want those non-dimensional terms to be small o of 1. So small o of 1 means that its magnitude will be at most of order unity. So we'd expect if one were to put in numerical values based on a solution of the problem, we'd expect those terms to have numbers maybe like 0.1, 0.5, maybe even 2 or 3, but nothing like 100 or 1000. So that's the meaning of small o of 1, that the magnitude of the term is at most around a value of unity. And what is the benefit of this? The benefit of such a procedure is that the resulting non-dimensional equations, you can tell the importance of terms by comparing the dimensionless groups that precede them. And we will see this in action now. So let's begin by scaling these equations as we said here. Okay, so how does one scale? Well, the algebraic procedure is simplest if you do the following. Instead of guessing at the appropriate scale for the velocity or the appropriate scale for the length, the easiest thing to do is to substitute characteristic scales and then look at how one can best make an appropriate choice. In some simple problems, of course, after getting a bit proficient with this procedure, it becomes much faster and you immediately know what scales to choose. But since this is the first example, let's just be explicit. So let us write the velocity u, the dimensionless velocity u, as the dimensional velocity divided by u characteristic. Or we could have equivalently written the dimensional u as its dimensionless remainder times the characteristic velocity uc. So the subscript c denotes the characteristic factor. This is a constant which we hope captures the magnitude of the velocity u. So by this, we can only do this roughly, of course, because we don't know the exact magnitude of u. Moreover, the magnitude of u, as you know, varies in the channel, maximum away from the walls, less near the walls, and so on. But roughly, we want to choose U characteristic so that the magnitude is captured. So yes, similarly, for the length, so for x, sorry, not x, for y, the cross-channel coordinate, we write it as a non-dimensional version of y indicated with the overhead tilde times a y characteristic, which really is sets the so-called length scale. And do we have any other variables? No, that's it. We just have u and we have y. Alright, this delta p by L of course are known constants. They should be viewed as parameters.